Today, we're going to discuss a very important topic in quantum mechanics, namely, what are the pure states of the angular momentum of the system? This is a topic, of course, that only comes up in multiple dimensions, and the way we came upon it was in our studies of trying to analyze to determine the allowed quantum bound states of the atom, thereby bringing our course back around full circle to where we began with Empedocles. Now, so far what we did in terms of thinking about the atom was we began to realize, well, it has rotational symmetry, which is something we then should exploit in order to solve for those bound states. And along the way, we defined the corresponding rotation operators and realized that the rotation operator around a given axis is very closely related to the corresponding components of the angular momentum operator, where the angular momentum operator, expressed as a vector, is defined in the traditional way as the position operator, expressed again as a vector, crossed then with the vector momentum operator. And that is something then that you can compute using your traditional determinant form of the cross product. You can carry out the corresponding calculations. We were particularly focused on the angular momentum about the z-axis, which you can expand out here if you like for yourselves. This is the result that we had previously. And the reason why we focus on the z component is not that the z direction is somehow special in space, but more just that when we think about spherical coordinates, the z-axis is the axis that's picked out special about which we actually build the angular coordinates in the spherical coordinate system. Because of that very special nature of z, it turns out that the angular momentum about the z-axis in spherical coordinates had a very simple expression that I've written down for you here. Finally, we then began to try to connect the total energy to these angular momentum operators, and we realized actually that it was the square of the angular momentum that was very closely related to the Hamiltonian. This led to an intricate discussion, the bottom line of which turned out to be that the Laplacian operator, which is the key term in our kinetic energy, which has a fairly complicated form in spherical coordinates with something kind of simple in the radial direction, and then this very complicated expression that appears in the angular coordinates, can be compactified very nicely as simply that radial part, and then all of these angular parts become very simple in terms of the square of the angular momentum operator. And by comparing these two expressions, we can actually pick out the form of the square of the angular momentum in spherical coordinates, as I've done for you here. Now, having understood the structure of the corresponding operators, the next thing that we realized is that we had a very nice opportunity here, because the coordinates in the system and in the Hamiltonian seem to separate out very nicely then in terms of purely radial parts and purely angular parts that have to do, again, with this angular momentum operator. That led us to attempt the standard procedure from partial differential equations of separation of variables, expressing then our many-body wave function, our pure state wave functions in terms of a product of a purely radial part and a purely angular part, which we called y. When we inserted this into the time-independent Schrödinger equation, we found that we were actually successful in separating out the angular parts from the radial parts, showing that these two equations separately must equal a constant a. And then when we set the angular terms equal to that constant, that's what I will be calling equation 1. That's where we will be focusing today, because we have so much information about angular momentum all out on the table at the moment. And then once we solve this equation and learn what the allowed values of A are, we will then set the radial parts equal to those allowed values, and that will finally allow us to solve for the radial components and thereby determine the allowed energies for the atoms. So the task before us today is to solve this equation 1, which I can rearrange in the following form by simply multiplying both sides by y, and we recognize immediately that this is telling us that our job is to determine then the pure states of the square of the angular momentum operator.